Yeah, hi everyone. So just to give you a brief introduction on what async is and what I'll be talking about, it's basically just this framework we have at Quora, which we use heavily for doing asynchronous fetching of data from memcache and Redis and other sources. And I'll go into a lot more detail on what that means, but I just wanted to mention that first because actually what I'm going to talk about for a couple minutes here is how like different mechanics of our product make this necessary. And then I'll start diving into details of kind of the problem that we're solving here and I guess like kind of why async is designed the way that it is. So what is Quora? Sorry, I'm in the wrong place here. Yeah, so basically we're a knowledge sharing product. We're mission to share and grow the world's knowledge. And I'm going to go through a few things here just to talk about how spread out our data is. Basically, like a lot of the problems that led to us building async have to do with the fact that like our data is not siloed like it is in some, especially like products where all of the data that you might use is relevant just to your organization or so on. But on Quora, you run into things where, okay, like here, this is like a lot of the data that you're seeing here is relevant specifically to this question that was added. But if you start seeing things like anybody in the world could have upvoted this particular answer here. The person who answered could have answered this, and they could have answered things about a ton of other content. So basically, we're looking at like a very large global data set, not completely unique to consumer products, obviously, but I do just want to highlight that first. And similarly, just see that like a lot of features throughout the product require pulling very different data from a global user base. So async. Basically, the motivation for async is that much of our data is stored on MySQL and HBase. That's where a lot of like ground truth data for us exists, and fetches from those stores obviously are quite slow. So you're not going to run into any consumer products where people are doing direct fetches like as the default for from MySQL or HBase. But they're very reliable and they're good places to persistently store data, and they scale quite well, or at least HBase does. So basically one solution here obviously is caching. You'll see this deployed all over the place. We extensively use memcache. We use Redis too. We use like actually a handful of other technologies for specific places where we need data fetches to be faster. So that sounds great. Like, okay, we'll take these things that were very slow to fetch. Those fetches were slow because the services themselves have to go to disk, or because of sometimes actually CPU to perform the lookups. And now we'll move them to these services where data is in memory and where the fetches are very fast. So this just gives you a sense of how long the full round trip of making an access from a web server to these different data stores look like. We're able to save like basically like 1 to 2 orders of magnitude by using caching extensively. Yes? Yes, that's correct. Yeah. So basically like the principle here is only go to MySQL in case of a cache miss. The miss rate that we experience is less than 5%. I've heard miss rates of consumer products, like depending on how exactly people configure their caching and how exactly those products are built and how likely you are to have a hit versus a miss. I've heard miss rates like significantly lower than 1%. So what a miss rate here means is how often do we actually have to fall back to MySQL, because not all of our data actually lives in the cache. So far this is stuff that like is pretty commonly deployed. A lot of like large consumer products will do some version of this, and as well as in many other sectors. So here we are with like a fairly standard setup. What's next? I'm going to talk a little bit about like different all of the data that you might have to fetch to render just even a single component of a page here, and how that might look with just like a network request per each piece of data, if that's what we were to do. So to render this particular person's profile and some details about them, this is just pointing out a handful of the things that we would need to fetch from data somewhere. So like we would need to get the URL for their profile image, send that down to the user. We'd need to get their name from some integer ID we have for them. We need to get their what we call a short bio. We need to get a follower account. So that's even just to render this very small portion of the page. We need, obviously, a lot of different types of data. So if you were imagining writing some code that was going to actually end up rendering that eventually, it needs to like fetch all of this data. So you could imagine doing that and calling all these render functions where they're fetching them from memcache, which is great because it's way faster than a full round trip to MySQL. But what we're going to run into here is that under the hood, each of these is making a request to memcache in this case to basically just wait for that data to come back. So if we step back a second here, if we're rendering the name here, we enter the render name function, we call mc.get, and now we wait on the network. So even though memcache itself is quite fast, and maybe the whole round trip just takes a couple of milliseconds, this web server could be doing something else. And you could imagine hundreds of different pieces of data that might be needed to render a page for a user. And if we're wasting 200 plus milliseconds just waiting on the network every time, then that's going to add up and actually become like very noticeable latency for someone trying to use the product. So yeah, this is what that might look like if this were like just a linear timeline where we serially wait each time on each memcache get. So obviously, like, if we step back and look at the information we actually need here, there's no dependencies between this information. So sometimes you run into a case where you could imagine that I end up needing to render someone's name based on the fact that they did upvote some answer and I only have an answer ID. Then there is a dependency there. I have to get the UID of the person that answered it before I can call something else. But in this particular example, we know all the information we need to perform all of these lookups before we even enter this function. So we don't need to be waiting on each of these requests serially. We'd much prefer to be able to fetch them all at the same time, and ideally to be able to do that in a way where people don't have to like manually specify those batches. So that's sort of the core problem that we're trying to solve here, is that we don't want these milliseconds to add up over and over again to the point where they actually become a problem for users. So a solution here is a batch get, right? So like basically every major caching service or really a lot of different forms of data services are going to support this. They're going to support some way to do a multi-get if you can actually in your application know that here's all of the keys that I need to get at the same time. And so if we can do that, then the memcache side of this might take a little bit longer than it would have previously. Here we're just like kind of talking order of magnitude levels here, but we've got maybe 1 microsecond that we're spending on memcache actually on that box and not just waiting on the network round trip. And so, okay, maybe if we fetch a whole bunch more things, now we're spending 10 microseconds on that box, but we're saving all of these milliseconds that we would have been waiting on these network round trips. So that's kind of like what we're trying to move towards. And so what I'm going to talk about next is how we were initially doing this, which once again, I think up to now, this is still something that like hasn't branched too much from how many people might solve these problems. These are common problems that come up in kind of like distributed web infrastructures. And we're about to get to a point where we'll talk about like how we solved this in the past, which is kind of a more, I guess, like simple way to solve it, and then building async, which is kind of the solution that we now have that makes it really easy to do this. So here's how we initially did this, and basically we required people to write a separate function, which we called priming function, to fetch all of the data they need to fetch, and then we would store all of that locally on the web server for the duration of the request. And so you can imagine basically people, if I'm a developer writing the code that's going to render that component we were just looking at, I have to both write this code and then I have to go write that code above, so that if I don't write that code, I'm going to be waiting a millisecond every time I call out to one of these underlying functions. But if I write that code first, and there's, this is sort of pseudocode, there's like our abstractions were doing something internally to store the data that was fetched so that when these try to fetch data from memcache, they don't actually go to memcache. So what happens there is we wait the 1 millisecond up there, we make sure that our application calls that function first, and then we drop through and eventually call this function, and now these all execute very quickly because they're just doing dictionary lookups in local memory for data that was already pulled in from memcache. So great, now we're in this place where we have caching, which allows our data fetches to go quickly, and we have batch network requests to decrease network round trips, and therefore, like, get to this point where we're just paying that cost a handful of times. And so one other thing that I will dive into, just real quickly, is remember that we were only able to do this because all of these are independent of each other, that we don't need kind of the output of one of them to call the input of the next one. So this, like, even a solution like this where you manually specify all of the batches that you need to fetch from the cache doesn't allow you to get to one network round trip. It allows you to get from hundreds to maybe like a dozen, because there's going to be some level of dependencies, and ideally we just batch all of those dependencies together and then deal with the next ones. And we did have an abstraction even before async for kind of like handling that, kind of executing different levels of our component tree, and finding, like, waiting until everything's blocked on some dependencies and then sending all of those priming batches out together. But the problem that we run into is that developers have to write most application logic twice. So as we saw above, you do have to write the actual logic that uses the data, obviously. And I don't know why I'm missing, okay, well, the other line here said once for the actual fetching of the data. So you'd imagine that basically every time you write any function, where here it's like pretty simple because there's not that many things going on. But if you have a function where you have like a lot of different branching logic, you basically actually end up having to mirror that logic in the priming function to know what data is going to end up needing to be fetched. And so you end up having like code in two different places. And we survived on this model for actually like quite a while by having kind of strict guidelines about your priming function should be near your other function. When you change one, there should be warnings about changing the other, and so on. But as you can imagine, this leads to all sorts of problems where eventually code branches, a bug gets fixed in one place and the other one doesn't change. And then all of a sudden now we're causing maybe serial memcache gets again, or maybe we're like, actually this logic is just wrong here because someone fixed a bug in just the priming logic and didn't realize it wasn't going to apply to the real logic that actually ends up rendering for users. So, so yeah, I'm going to do a brief detour on Python generators because just to make sure that like everyone's kind of got enough familiarity to talk about exactly how we're going to use async coming up. I just want to kind of do a brief example there. But basically Python generators are what are going to allow us to avoid this code duplication, but still get the batching that we need to make sure that requests can be really fast. So here's just an example with just kind of obtusely named variables, but my intention is just to walk through it line by line to give you a sense of what's happening here. So so actually, even before I start talking about that, the overall, like, one not perfect way to describe generators, but a quick way to understand them is that like a function that is not a generator like allows you to like send input to it once and receive output from it once. A generator roughly allows you to do that many times. So it's possible for a generator to introduce this, to use this keyword yield, basically just to kind of send data back to the caller before it's actually done running. And then the caller can optionally also send data back to the original function, which will be what the expression yield, like its value is whatever the data was sent back from the other function. So, so just to step through that really quickly, we define this generator over here. If we say object equals gen of 10, then basically we we're sending 10 to arg over here, and we yield arg times 2, so we're yielding 20. And what that yield does is that it sends it back to any time that the caller calls object.next. So now v1 becomes 20 because it's arg times 2, which means that now g1 is 20, and now we're yielding 20 plus 1, which is 21, and then we like send back that v2 becomes 21, and we send back I think I missed a step here, but the point is that we're having this like back and forth, and the point's not so much what the actual value is at the end, yeah, hopefully that makes some amount of sense. Like basically what's happening here is if you look at each line here, it's actual communication back and forth from the function or from the generator, excuse me. So back to async. So basically, like, we would like to be able to use that syntax to allow a bunch of our functions to get just to the point where they actually need data, and then tell us that, like, tell some scheduler or tell some code, some framework that's running somewhere that, hey, I'm blocked on some data. And so instead of in kind of the priming world or a world without generators, if we did get to a point where code was actually trying to directly make a request out to memcache or make a request out to some other data store, then like we don't know about that. We just sort of like, it talks directly to the client library and then talks to the network, and it's just waiting on the network. So we'd rather introduce this layer of indirection where we say, okay, you know you have to wait on something, wait on our library, and then our library will figure it all out for you. So here what we've done is we've changed what used to be, the name used to be a memcache get, but now we're yielding a future which has this key for the particular username. And so basically we're telling our library underneath, like, hey, this function needs this data, and can you like do whatever you need to do to get it this data, and then when you have it, you should send that data back as the result of this yield. So great, like that's, you know, we could kind of, under the hood, we could just implement this as actually just an immediate memcache get that just sends it back, and it would be exactly identical to the old code, but we're gonna do something a little bit better than that. We also have this async decorator that collects all of these futures and helps with some of the scheduler underneath. But so what is the scheduler doing then? So this is just like a pseudocode example of if we wrote a scheduler just for this function, and if we did what I was talking about just a second ago, where we end up actually just making the request to memcache. Here, like, we get the exact same result of what we had earlier, with just like an additional step in between where you're kind of like yielding out to the scheduler, and then you send that result from memcache back. So okay, that's not helping us so much so far. So where do we go from here? Basically we want to do this like for all of our different threads of execution. So as I mentioned earlier, we already have a framework that allows us to render different components that are independent of each other, kind of to different levels of the tree until they get blocked on something. And so in this case, we just let them all get blocked on our async scheduler, and then we're able to look at this, where we yielded this future here of like the particular key of data that it needed, as well as like what data stores. So this is still a little bit oversimplified, but basically the scheduler is able to get to a point where like, okay, now literally every thread of execution that I know about has yielded to me. I'm using the term thread loosely, by the way. I don't mean like Unix threads. I mean like an abstract thread of execution. They've all yielded to me. They're all waiting on data. Now I can look at, okay, I've got 50 different items that are needed from memcache, and maybe I've got another 10 over here that are needed from Redis, and a few from HBase, and let me just like kind of package all of those up and just send 3 network requests. When they all come back, then I can do this gen.send on all of those generators. So basically it's just a scheduler that's keeping track of all of these different these various different threads of execution and what they're waiting on, and with the important thing being that many of those things are waiting on data from the same data store. So we're able to benefit from the same thing we were with priming, where previously we were manually instrumenting these like multi-gets to like say, okay, like let's go like get all these things from memcache specifically, and maybe we had these things from Redis specifically that we needed. But now we just have this generic scheduler that's able to know what things can be batched together and what can't, and so on. So stepping back to our example that we've been playing around with a little bit too much here, before we were just calling all of those functions directly, but what does this code look like actually? Instead of using this kind of raw generator syntax directly and having to have like kind of particularly obtuse looking schedulers for each of them, we're able to basically just yield out all of these different functions which end up returning these futures. And so by decorating it with async, the Python decorator allows us to kind of like get in between the return value here and the actual return value of the function. So our async decorator is able to see all these futures were yielded out. It's able to treat the function as a generator, and then send those to the scheduler appropriately. The important thing being that like, does this code look that much different from this code? Like it's, like yes, there are syntactic differences, but structurally it's very similar. Versus if you compare it to I guess some of the code like where you're actually having to directly use yields underneath, those things are changing quite a bit. So so basically like I can use this as a user without really knowing what async is doing. I can I know that async exists to help me get all my data. I know that that's how I get data at all, because like maybe priming doesn't even exist anymore, and maybe I don't let you call the memcache library directly. But I can kind of write code very similarly to how I would write it, even if I like wasn't even thinking about this problem. So the basically underneath the exact same thing is happening as we were talking about before. We have all these MC gets that end up happening, and it allows us to batch logically distinct units of code. So like before we had to be smart about okay, we gotta know what's gonna call a prime function where in order to call all of those prime functions and batch them appropriately. But now we can actually even step completely outside of our web framework, and maybe something needs to be happening that's not literally just rendering view code for a user, which also needs to talk to these data stores. And we can execute that code too and let it benefit from the same batch requests out to the same data stores. And so another example, a specific example of that is that email pipelines is something that previously we had zero batching for at all, because it's just kind of early on when you're thinking about what needs to be fast in your whole infrastructure. Obviously rendering a request that a user is waiting on right now is going to be something you're going to prioritize first. And if email pipelines are slow, so be it. We'll that's a problem we can deal with later, because there's not a user literally waiting on that email right now usually. But basically by having this kind of generic shared library that just sits on top of the APIs that the email pipelines were needing to use anyway to get their data, we were able to with very little effort batch our email pipelines and speed them up by several orders of magnitude actually, so that basically the cost of constructing and sending email at Quora goes way down because we're able to do it with fewer boxes. And yeah, it's built to be a general purpose framework. And it is something that we've threw on GitHub, I think 6 to 9 months ago. So it's something that is meant to be general purpose and could be used for your application as well. So this is just sort of a graph to, or a diagram to give you a sense of overall what's really happening here. We have these different dependencies that are happening maybe in kind of independent parts of our application that all get to a point where they're waiting on memcache keys in this particular case. Async knows about all of that, calls this multi-get, and then yields the results back to all of those dependencies, which then are able to return their results to some root call. So yeah, a few side notes before I open up for any questions that you guys might have. A common question is how this relates to async IO. So we actually initially built this for Python 2.7. Our application these days is now 100% on Python 3.6. But when we first built this framework, or started building it about a year and a half, 2 years ago, we were mostly on Python 2.7. And so it was important for us to to be able to implement our scheduler, even in cases where async IO would have been able to help us. But as we moved our code to Python 3, we were able to get kind of I think an even more proven answer of this question, which is what our initial thoughts were here, is that async IO helps a lot with the scheduling part of this. But actually the majority of the code that we worked on was around the APIs to make this really intuitive to use. And to kind of one way to think about it is like a constrained API where you can't do as much, obviously, as you can do with a general purpose tool like async IO. But where it's really easy to use for the specific applications that we're building it for. A few adventures with making this intuitive. So for some background here, at Quora, basically we have developers with a very wide variety of backgrounds. So in particular, there's some other examples too, but basically a lot of people at the company code. So we have a design team with a lot of folks who some of whom had never touched Python before they joined Quora. And we build a lot of frameworks to make it really intuitive for them to ramp up on that quickly and to be able to kind of prototype their own designs. So an important kind of design constraint for us, and why we cared about, a big part of why we cared about constraining the API and the way I talked about a minute ago, is that designers be able to dive in and use it and not have to think in too much detail about sort of everything that's happening at the system level underneath. And yeah, there are also people in other roles at Quora who drop down to code occasionally, and the easier we can make that for everyone, the more effective the whole company is. So yeah, several API decisions were aimed at making this easier than priming before, where you'd imagine, okay, why do I have to write this code twice? I don't even really understand why I'm doing this, versus just making it this is the way that you fetch data. And there's sort of no wrong way to do it. You can't you can't accidentally create all these serial network requests. Yeah, and then just one quick fun story along those lines is that a common kind of gotcha that people were running into when we started introducing this, and when especially for people kind of closer to the view side of our code base who had never really touched generators in Python before. Basically through Python 2, it was just a constraint of Python that you could not return from a generator. So once you've kind of decided that this is going to be a generator, you can yield from it, and that's how communication works. And there are good reasons for that. But basically, at the end of the day, we looked at how many times people were running into these gotchas, and we said, and we also looked at the fact that the Python 3 world has already kind of landed in a place where it's okay to return from generators. And we said this is not worth it. It's too many people get kind of held up by this problem all the time, don't really even understand what's going on. So actually someone basically just looked into how did Python 3 handle this, saw that it was kind of just remove that constraint, and went and patched our Python 2 interpreter to do exactly that, to allow returning from generators. This is not a solution that I generally encourage. It's something that part of why we were okay with that solution is we knew that we were moving to Python 3 in the near term, and so we weren't going to be on this crazy forked interpreter of Python for too long. But yeah, it's just sort of a fun side note, basically about some of the sorts of things that we try to do to make this as intuitive as possible for users. But yeah, and then one final side note is on migrating a large code base to really any new API. I think this was, we'd done a handful of migrations like this where we change how you do something fundamental in our Python code base. And if you do it in a way like we did with this, where we said, okay, we want to completely get rid of the old model so people never have to think about it again, you basically either people have to be doing a ton of repetitive work, which is no fun for anybody anyway, and often actually adds up to be way more work than coming up with a more clever solution. So what we found here is like, okay, let's just like make heavy use. We already have like a static analysis library that's like aware of a lot of our abstractions and is able to kind of like do more than just a very generic abstract syntax tree would. And we were able to build scripts on top of that to automate a lot of this work. So basically that work that I showed a second ago, we're like, okay, what does this function look like now that we're going to use async rather than just calling through to functions underneath? Where, you know, it's nice that that looks similar for the users, and that's actually why it was designed that way, is because like it should feel really similar to developing without async. But it actually also makes this much easier because like now the code like actually is structurally very similar to what it was before. It's relatively small changes. If you're having to manually go through and make all those changes, you're going to get tired of it very quickly, but a script can actually do it quite effectively. And we were able to build these scripts that make those changes, and then people like were just able to like verify that what the scripts did looks reasonable, and sometimes like rename some intermediate variables that were introduced to be something like reasonable. And so yeah, we found that like even including the time to develop and make these scripts kind of like robust to our entire code base, we definitely saved more than half of the time that we would have otherwise, and it's something that that I think like we're continuing to apply to future migrations. So basically you can learn more at, we do have a more detailed blog post about some of the implementation. So especially like this goes into a little bit more detail on the scheduler than I did here. And then for a lot more detail, you can see the code on GitHub at github.com/Quora/async. That's async with a Q. And yeah, that's it. So love to open up for any questions you guys might have. Yeah, so it actually was less than we expected, but I think there's a few reasons for that. So we had like made some initial estimates, like actually several over time, at migrating to Python 3 in the past, and had kind of concluded it was going to be this huge thing. And a lot of the reasons that were contributing to those initial estimates were, here are libraries which don't currently support Python 3 that we're either going to have to find alternatives for and migrate all our use cases, or here are libraries we're going to have to like re-implement entirely ourselves. Like there's especially a bunch of small ones, things where people are just wrapping some REST API that we happen to use and no one has bothered to maintain that library. We like maybe have to go back and either rewrite or at least migrate it ourselves to Python 3. And actually by the time, because when we initially started looking seriously at migrating to Python 3 and making a lot of these kind of estimates, that was maybe 2 or 3 years ago. And it was like definitely before the majority of like open source libraries and communities had like entirely moved their code bases. So we did sort of benefit from being on the later end here, and that we moved within the last year. And then when we go back and look at some of these things, we're like, hey, this library now supports Python 3. We got that for free. So that was one of the bigger benefits. But even the other things that we estimated around migrating our own code, we were just able to automate it a lot more than we expected to be able to. I think the biggest thing that was roughly about as complex as expected was dealing with byte strings and Unicode strings, which like probably won't surprise people that have dealt with that sort of migration before, but I think yeah, at the end of the day, like by kind of defining the places where we were absolutely not okay with those things breaking versus places where we were okay with responding to them as they do break, we were able to not have to comprehensively, literally go through every string in our code base and make sure that it would work. And so yeah, I mean, in the end, like the migration in earnest took like around a month or two for a team of 4 or 5 people on a pretty large code base. And a lot of that is because of the automation work that they did. So yeah, like at this point, I would say like I'd absolutely recommend it. There are a lot of benefits you get out of being on Python 3, obviously, and I think a lot of the costs in the past are in the past, and now that like kind of the ecosystem is more fully supporting Python 3.
Yeah, I had a question about async, and so you use it with memcache primarily.
Yeah, and
Have you used
Redis.
it with like SQL Alchemy? Does it work with that?
So we haven't directly built support for SQL Alchemy, but it is built to be extensible. So because we've built, since we initially built and deployed it, we've actually built a couple more plugins for it for like other small data stores that we use. And it's yeah, so it's built to allow you to do that. You basically just like make the calls out to like whatever your API is that ends up fetching data. You have to like write those calls yourself and then implement it as a plugin. But and then all of those, everything's batched by particular data stores. So if you're using SQL Alchemy heavily, then you could get away with that. So I'm not super familiar with SQL Alchemy in particular, but one thing that we've run into is since we use I guess like a less intelligent and less complex like MySQL library. And for batching those, I think we could also get some benefits from batching MySQL calls. But they're fundamentally a little bit more difficult to batch than memcache, because memcache is literally just, here's a key, give me a value. Like, for batching MySQL, you need to make sure it's like on the same table, and that maybe changes the where clause and maybe makes it like a lot more complex. And maybe SQL Alchemy already handles that well, but yeah.
Yeah, you can use the filter by keywords to get
Yep.
information on that. But my interest was in batching reads to get information.
Yeah, and I'm sure like if SQL Alchemy is makes it easy to take two queries and turn them into one, then you could definitely write a plugin for async, which would allow you to just plug into that functionality of SQL Alchemy and then have your application not have to manually like call that itself.
Thank you.
Yep.
What would need to change when you move to async IO? I mean, I know it works as is, and it's probably very similar, but I mean, I'm just curious, like, what would you actually be changing? And is it just to be compatible, or is it actually adding some features for free that you otherwise didn't have?
So yeah, if I'm understanding the question correctly, like basically, like all that has changed for us as we've moved to Python 3 is like moved now 100% to Python 3 is that we can use async IO like instead of some of our manual scheduling logic that we had previously. But like a lot of the code that we've actually implemented is sort of like stuff on top of that allows things like plugins to client libraries that don't support asynchronous IO and batching, and things like the API that like the decorator that kind of like handles all of this like the actual glue between the different generators. And like I guess like the futures and things like that. So I think of this as like a layer on top of async IO, even though it was not originally built that way, with like a portion that we implemented initially that we could just throw out and replace with async IO.
So now that you've done the migration, is your code base easier to maintain? I mean, you obviously got some performance benefits.
Yep.
But is your code base smaller and easier to maintain?
Yeah, absolutely. So I forget what the like even order of magnitude of the number was, but someone like after the migration was complete, like looked at just like the diff of number of lines of code because of taking away all this duplication, and it was like a shocking number. Like definitely tens of thousands plus, and like I don't even like it might have been like even a higher order of magnitude because it is pretty big. So that's one thing. That's just like a raw number that is shocking. But I think like the other thing that we found is that a lot of the sorts of bugs we ran into in the past with especially performance issues that we ran into, like we just don't even see at all anymore. So these are things that like it would like a page would suddenly get slow, and it's because someone changed the logic without changing the priming function. And then you got to like go track down exactly which one that was, and each of those maybe takes an hour like to completely figure out. And then even though the fix is really trivial, and that's gone away completely now. And then just like anecdotally, like people who have been around since before we did the migration are like do comment that it's just duplicated code they don't have to write anymore, and that saves them some like like hard to quantify amount of time. So So yeah, I mean, I would say yes, although it's hard to quantify exactly how much.
You mentioned that you didn't use async IO because you didn't work with Python 3 at the time. Could you use Trolleus because it was available as a third-party package backport to Python 2?
Sorry, what was the?
Trolleus was the package that backported async IO to Python 2 back 3.5 years ago at least.
Oh, interesting. Yeah, I'm actually not familiar. At the point that I got involved in the project, it was after like we'd already decided to like build out our own scheduler. So I'm not familiar if people were aware of it and decided not to use it for some reason, or it's possible they were just unaware of it.
So when you migrate to Python 3, a potential issue is that your memory consumption could go up. Was this significant? Did anybody, or did you happen to monitor that?
Yeah, so it was definitely a concern. Interestingly, at almost exactly the same time, we were also moving from 64-bit somewhere to 64-bit everywhere throughout our infrastructure, which like a reason that, so compared to 32-bit Python, and a reason that we'd held off on that was memory consumption. And so that actually kind of overwhelmed any of the memory concerns we might have with Python 3 because it's just like that change of doubling pointer size is like way bigger. So yeah, I mean, but a lot of the approaches we took for like, I guess the net effect of both of those changes around the same time were to just like kind of offset it with other improvements to memory size and to like also, I think we actually saw some CPU usage increases, which surprised us, not on 64-bit, but on Python 3. And we mostly took an offset approach. So we do things like our local, like within process caching library, we were able to like find some optimizations there that offset some of it. But like it especially, I think part of the reason we took that approach is because when you're looking at a move to 64-bit everywhere, there's just no way around that. Like that's like pointer sizes are going to get bigger. There's a bunch of pointers like you're gonna use that much more memory. So if you want your memory size to be smaller, then you're gonna have to find other ways to do it. And fortunately, we were able to find some, and then we were able to also kind of agree with like some of the people that work around our infrastructure costs that like we were willing to spend a little bit more on more boxes with more memory. So.